Every time you fire off a text, make a quick call, or stream a video, you're basically sending a message on this invisible, super high-speed journey across the globe. Today, we're going to pull back that curtain and actually follow the message on its incredible trip from your screen all the way to the other side of the world.
So it really all boils down to this one simple question. How in the world does a message, your voice, a text, just defy distance and time like that? It feels like magic, doesn't it? But it's actually this brilliant chain of engineering solutions, and we're going to trace the path of that single hello from the very beginning to the very end.
All right, so the very first step in this whole journey is translation. The world we live in, the world we experience, is analog. It's smooth, it's continuous, kind of like the sound waves of your voice. But computers, they don't speak that language. They speak in numbers. So first things first, we've got to convert our message into a digital format.
Okay, what I love about this slide is how it just perfectly visualizes the core difference here. An analog signal, over on the left, that's a perfect smooth ramp. It has an infinite number of points all along its slope. The digital signal on the right, though, that's a staircase. It gets close to the ramp, it approximates it, but it does it with distinct, measurable steps. Our entire goal here is to turn that ramp into a staircase without losing the meaning of the message.
Now, this whole conversion thing is like a three-step dance, and it's called pulse code modulation, or PCM for short. First, we sampled the signal. That means taking thousands of little snapshots of it every second. Then we quantize, which is just a fancy way of saying we give each of those snapshots a numerical value. And finally, we encode those numbers into the language that computers understand best, binary, zeros and ones.
So let's zoom in on sampling for a sec. The best way to think about it is like a movie. A movie is really just a bunch of still pictures, right? But when you show them really fast, you get the illusion of smooth motion. Well, sampling does the exact same thing for a sound wave. It captures its level at thousands of these super precise moments in time to build a digital picture of the sound.
All right, next up we've got quantization. Every little sample we just took has a really precise value, but there's a nearly infinite number of possibilities. That's too complicated. So quantization simplifies all this by basically sorting each sample into the nearest predefined level. It's kind of like rounding a number to the nearest whole digit. Now, this step is absolutely crucial, but here's the catch. It's also where a tiny bit of error, something we call quantization noise, can sneak in. Okay, so now our message is a neat little stream of zeros and ones. Easy, right? Well, not so fast. Its journey has really just begun, and let me tell you, the path is full of obstacles. It's like an electronic obstacle course out there, and our signal has to make it all the way through without getting messed up. In this story, our signal has two main villains it has to fight. The first is random noise. You can just think of it like static, or an electronic hiss that can randomly flip a 1 to a 0. The other one is a little more sneaky, and it's called inter-symbol interference, or ISI. Think of ISI like this. You're shouting in a canyon. The echo of your first word starts to blur into your second word, and pretty soon, everything is just a jumbled mess. That's what happens with digital signals. The energy from one bit can actually smear into the next one, totally confusing the receiver about whether it's looking at a 0 or a 1. It is a huge, huge problem for high-speed data.
So how do we fight back against this mess? Well, this is where engineers use some incredibly clever tricks. On the sending side, they use something called pulse shaping to carefully design the signal's waveform. Imagine shaping it so that each bit hits its absolute peak just as its neighbors are at 0. That completely avoids the smearing effect. Then, on the receiving end, a matched filter acts like the perfect key for that very specifically shaped lock. It's designed to recognize that signal shape even when it's buried in a ton of noise. It's brilliant.
Okay, so we've got this super clean signal. It's ready to go. But it can't just walk out the door, especially if it's going wireless. It needs a ride. It needs to be put onto a high-frequency radio wave that can actually travel long distances through the air. And that's where a process called modulation comes in. We take our baseband signal, that's our stream of zeros and ones, and we use it to change, or modulate, a property of a high-frequency carrier wave. This carrier wave is the vehicle. This one idea is the fundamental principle behind basically everything wireless: radio, Wi-Fi, your phone's data connection, you name it. And this table just lays it out beautifully, the three basic ways we can do this. With amplitude shift keying, or ASK, we change the wave's height or intensity. Think of a dimmer switch. With frequency shift keying, FSK, we change its speed or pitch, like a high-pitched whistle for a 1 and a low one for a 0. And with phase shift keying, PSK, we shift its starting point or pattern, kind of like changing the rhythm of a drum beat. Each one is just a different kind of secret code for putting our ones and zeros onto that carrier wave.
But just getting a clear signal isn't enough anymore. Modern systems also have to be secure and super reliable, especially when you've got millions of people trying to talk all at once. And that requires a little bit of communication magic. The key idea is captured right here in this quote. If you want to make a message really hard to detect, or hard to jam, or hard to interfere with, you don't shout it. No, you spread it out so thinly that it just blends in with all the background noise.
This technique is called spread spectrum, and it's kind of a genius move. It takes our nice, tidy, narrow signal, and it deliberately smears it across a huge range of frequencies. Now, to anyone else who's listening in, it just looks like random static. It's meaningless, but the intended receiver knows the secret pattern. They have the key to perfectly reassemble the message.
So why is this such a huge deal? Well, spread spectrum is literally the tech that makes our modern world tick. It's what makes your GPS so incredibly accurate. It's what allows so many cell phones to share the exact same frequency at the same time, a technology you might know as CDMA. It is an absolute cornerstone of secure, modern communication. So we've walked through this incredible chain of solutions, right? But underneath it all, there's this one fundamental truth, this one constant balancing act that every single communications engineer has to deal with, every single day.
And here's the simple fact. You just can't have it all. There is no single best or perfect way to send a message. Every single design decision is a compromise. It's a trade-off between things you want but can't possibly maximize all at the same time.
And this chart? This is the classic communication triangle. It's the balancing act every engineer faces. For instance, do you want blindingly fast speed? Okay, you might have to accept more errors in the data, or use a whole lot more power. Do you need perfect, crystal clear, error-free communication for a critical mission? Well, you're probably going to have to sacrifice some of that speed. What if you need your phone's battery to last all week? Well, then you definitely can't be transmitting at maximum speed and power. See? It's always a trade-off. And this isn't just some minor detail, folks. This is the job. In fact, a huge part of what a communication engineer does is simply manage these trade-offs, balancing speed, clarity, power, and bandwidth to perfectly fit the needs of whatever application they're building. So when you think about it, from a simple sound wave to a number, through a gauntlet of noise, catching a ride on a radio wave, and then hiding in plain sight, the journey of that simple hello is just this beautiful, elegant sequence of problem solving. It's all about turning our analog world digital, protecting it from getting corrupted, and then managing the fundamental limits of physics to get it where it needs to go. And that really brings us to the final big question. As we demand faster speeds, more and more connections, and greater efficiency for literally everything, from self-driving cars to virtual reality, the pressure on this chain of solutions is just immense. So what do you think the next great engineering trade-off is going to be? And what brilliant new solution will it inspire?